Welcome back to Multivariate Calculus. In this video, we're going to be talking about arc length parameterization. The idea here combines a couple of ideas that we've talked about previously. First of all, reparameterization. We have seen in the past that when you define a curve parametrically using a vector-valued function, that there are infinitely many different functions that define the same curve. The changes may occur to the interval of time or whatever step you are talking about that you use to describe it, but the curve is the same. And we've used that in the past to think about in kinematics the difference between tracking steps in time, tracking steps along a horizontal axis, or tracking steps along a vertical axis. Now that we have the idea of arc length at our disposal as well, this introduces a new option that I think is incredibly obvious. That is the arc length parameterization. All right, so let's start with an arbitrary curve. And again, we're thinking about this in space. In time steps, it could be that some of the steps are relatively small and other steps are relatively spread out. A very simple example here, think about an object falling. If you understand basic kinematics, you know that an object falls at an accelerating rate. So each step in time, the object will fall a greater distance than it had in the previous step. And while sometimes that is incredibly useful, it does make several things we might want to analyze somewhat challenging. So instead, our goal is to divide up the curve into steps of equal length. So we have seen that if we have our function, our vector valued function parameterizing the curve r of t, we can come up with the arc length function s of t using this integral. If it so happens that you can solve that equation for t, then instead of having s as a function of t, you have t as a function of s. And if you can evaluate r of t of s, then you have r as a function of s. And that is the arc length parameterization. Each step in S will be an equal arc length. Sometimes doing that is very straightforward. Consider, for example, the curve that we've already been studying. Cosine 3t I hat minus 4t j hat. Why do I always leave the j hat out? Minus sine of 3t k hat. I'm really writing faster than I'm thinking today. Nothing new there. Right? Cosine 3t I hat minus 4t j hat minus sine of 3t k hat. And we've already seen that the arc length parameter or the arc length function for this curve is that s of t is equal to 5 times t. Equivalently, that means that t is equal to 1/5 s. And so I can write that r of s is equal to r of t of s, which is going to be the cosine of 3/5 s I minus 4/5 s j minus sine of 3/5 s k. And the reason that we care about this is that the arc length of this for s in the interval from 0 to some ending point that I'm going to call p is p. Straightforward, that's it, we're done. Okay, if we can do this, then it is easy. How hard is it to do this? Well, let's take a look at an example that doesn't seem to be all that difficult. Um, for simplicity's purpose, I'm going to go from a three-dimensional curve into a two-dimensional curve. And let's look at a two-dimensional curve with which you are incredibly familiar. Y equals x squared. Right? Parameterizing this curve is fairly straightforward. We've done things like this before. R of t is going to be a vector in 2 dimensions. We have the curve written y as a function of x, so it's going to make sense to set t as our x component and then plug that in. Y of t is t squared in our y component. We can take the derivative of this thing, r prime of t. Well, the derivative of t is 1. The derivative of t squared is 2t. And we can find the magnitude of that derivative. It will be the square root of 1 squared, which is 1, plus 2t squared, which is 4t squared. All right, so all we have to do is calculate the integral from 0 to t of the square root of 1 plus 4 tau squared d tau. That shouldn't be too hard, right? Right? This integral is an integral that we've learned how to deal with in the past. It can be solved relatively readily using a trigonometric substitution. But if there's one thing that sticks in the brains of students after the second semester of calculus, it's that I really don't want to do a trigonometric substitution ever again in my life if I can avoid it. And that's why we have the tool of integration by table. So I'm in our OpenStax textbook. I'm in Appendix A, the table of integrals, and I'm simply going to scroll down for a while. We've got what are called the basic integrals. Those are the ones that you have memorized or probably written down at ready reference. And then we get into the trigonometric integrals, which are not of any help here because we don't have any trig functions in our integral. Likewise, we don't have any exponentials or logarithmic or hyperbolic functions or inverse trigonometric functions. So we want to scroll down past all of that until we get down to this heading, integrals involving a squared plus u squared, where a is greater than 0. And this is starting to look promising. In fact, that very first one looks kind of promising to me. So in our table, we're looking at number 68, which says that the integral of the square root of a squared plus u squared du is equal to u over 2 times the square root of a squared plus u squared plus a squared over 2 times the natural log of the quantity u plus the square root of a squared plus u squared plus constant of integration, but we're going to be dealing with a definite integral, so that's not strictly necessary. Nonetheless, I've copied that whole thing down. And now I'm playing a matching game. If I set a as equal to 1 and u as equal to 2 times tau, then a squared is 1, u squared is 4 tau squared, and we have the stuff under the square root exactly how we need it. But then, of course, if u is 2 times tau, then that means that du is going to be 2 d tau. So we have to deal with that by putting a factor of 2 out here. I'm sorry, a factor of 1/2 out here and a factor of 2 in there. And now I have the 2d tau that I need to make my substitution. I am now looking at the integral from, well, when tau is 0, u is also 0. And when tau is t, u is 2 times t. But then I have the square root of a squared plus u squared du. And that means that I can use this formula and get the result here is going to be u over 2 times the square root of a squared plus u squared plus a squared over 2 times the natural log of u plus the square root of a squared plus u squared. And at this point, I realized that I made a big deal about putting that 1/2 in front of my integral and didn't actually put that in front of the integral. So let's correct that. All right, so I can replace a with 1 in both cases, and I can plug in my limits of integration, and that will give me my solution. So I've got 1/2 of 2t over 2 times the square root of 1 plus 2t, the whole thing squared, is 4 times t squared, plus a squared, which is 1 over 2 times the natural log of u is 2t plus the square root of 1 plus 2t, the whole thing squared, which is 4 times t squared. And then subtract 1/2 of, now u is 0, but we do still have to write the whole thing out just to make sure. We have 0 plus the square root of 1. Natural log of 1 is 0, so this whole thing goes to 0. That's a relief. When you start looking at the curve, it has no length. That is important. That's incredibly useful. But it doesn't always have to work out that way, because sometimes this first bit would have an extra component in it. So it is always worth taking the time to check that, especially as things get complicated. All right, so let's see what I can try to simplify here. I have that s of t is going to be 1/2 times 2t over 2, which is just t over 2 times the square root of 1 plus 4t squared plus 1/2 times 1/2 is 1/4 times the natural log of 2t plus the square root of 1 plus 4t squared. Okay. If I can solve this equation for t, then I will have the arc length parameterization that I was looking for. But it turns out that it's actually impossible to solve this equation for t. First of all, why is it impossible? This equation is what's known as a transcendental equation. If I scroll the screen a little bit, hopefully I can get that, yep, there we go, to show up above my head so I can talk about it. Notice in this equation, I've got s way over here. That's not anything to worry about. That's just s. Then I have t in an algebraic expression plus t inside the argument of a logarithm. I've got t inside the argument of the logarithm, and I've also got t outside of the argument of the logarithm. Logarithms are transcendental functions. Transcendental functions are most notably characterized by the fact that they cannot be handled algebraically. And because of that characteristic, it's actually impossible to solve an equation analytically that has t inside and outside of the logarithm. It just cannot be done. The same is true of exponential functions, trigonometric functions, hyperbolic functions, inverse trigonometric functions. Whenever you have the variable you're trying to solve for both inside and outside of the function, it's unfortunately never going to be able to be solved. So what does that mean for us in this particular circumstance? It means that as nice as it would be to find an arc length parameterization for the curve that we're looking at, it might just not be possible. It might just be that we can't do it. And there are certainly circumstances where we can. We've seen an example where it's pretty straightforward, but there are far more examples where we just literally cannot. All right. Let me get my head out of the way, make sure I'm pushing the right button. And I'm going to finish with a problem for you to take a look at. Here is the parametric curve that you studied in the previous video. R of t has components 5t, 3 times the sine of 4t, 3 times the cosine of 4t. And so you already know s of t. So what I want you to do is twofold. First, write the arc length parameterization of this curve, r of s. And the second thing that I want you to do is calculate the norm of r prime of s. Seems kind of circular in its logic, but take a look at it, see what you get there. And then I'll see you in the next video.